Hello everyone. My name is Pedro Cumin. I'm a PhD student at the Universidade de Aveiro, Portugal, and I'm Marie Curie's early stage researcher of the Team Up 5G project. And today, I will present this proposition paper entitled Flying Mobile Edge Computing Towards 5G and Beyond, an overview on current use cases and challenges. And this is my agenda for today. I will firstly give an introduction to the scenario I am studying. Then I will show the main applications and the characteristics of the study architecture. Then I will present the current state of the arts. And finally highlight the open issues and views. Nowadays, we are currently facing the growth of more and more highly computational devices and the emergence of sophisticated service and applications as well. It brings challenging requirements to the network, what includes reliability, latency, battery lifetime, quality of service, quality of experience, and so on. For these reasons, in order to mitigate these requirements, the 5G generation comes to mitigate the most diverse challenges inherent to the current dynamic mobile networks and their increasing data rates. And the employment of small cells building a ultra-dense network comes as the standard approach to fulfill the current network requirements. However, the densification of small cells leads to line-of-sight link limitations and lack of adequate infrastructure both in urban as well as in remote areas. The employment of UAVs in such scenarios is very common as we have demanding applications and services in hard-to-reach areas. Even more challenging is the support of flash crowd events. That is when there is an increased data rate requirement. One of the promising benefits of 5G networks is to get immersed into an environment, in, for example, a stadium, where for instance, in a soccer stadium, for example, users are limited to the perspective from where they stand throughout the entire game, instead of having the possibility of freely select a viewpoint they find interesting. In a concert, for example, they need for high bandwidth communication to share videos and video lives and our visioned services. Uh, what usually require is a temporary strong network to handle this, and UAVs will be able to extend and increase the capacity of the backhaul network for this crowd and sudden events like these ones. UAVs can also work as aerial base stations to provide promising solutions to enable fast, flexible, and reliable wireless communications in public safety scenarios, disaster-affected areas, or as a network of aerial sensors to collect data in large areas. The information gathered in real-time surveillance and monitoring scenarios, or even post-disaster recovery, must be sent and also processed in order to the information generated in order to obtain an accurate as possible information from the data and as fast as possible. In most cases, the cloud computing is not reachable via a direct link. Thus, taking into account mobile computing, paradigm the use of multiple UAV. And here are some of the main reasons to employ UAV. They are cheaper and faster. They are highly flexible. They can be employed on demand. There's no highly physical constraints like as they fly. So And the employment of multiple UAVs is even more advantageous as it provides a broader coverage area. Is with multiple UAVs, we can establish a backbone integrated with ground stations or another available resource, computational resource node, and we can reach a better scalability when using more than one UAV. Another feature that is important is a multi-tier architecture that brings better scalability, reliability, information delivery, network formation, and management. And the multi-tier UAVs architecture alleviates the trade-off between line of sight and path loss. And it means that um, the higher the altitude of a UAV, the greater is the possibility of have an air-to-ground communication link, since there is a higher probability of line of sight. However, the increased distance between a UAV and a ground node also increases the path loss, and the trade-off between the coverage of a UAV and its distance to the ground mobile users is an issue that a multi-tier UAV architecture can mitigate. So a multi-tier architecture employs UAVs with different mobility models, where the stationary ones fly in a lower altitude, provide cover to uh, in a lower altitude, and the more dynamic ones fly in a higher altitude, providing coverage to UAVs in the lower altitude. And the UAVs in the lower altitude provide connectivity or the different services to the users or to the nodes on the ground, and can be seen in this picture. We have a more dynamic UAVs in the upper tier and more stationary UAVs in the lower tier. So in here we have the ones responsible to um, manage the other UAVs, and the UAVs in these tiers are responsible to connect to the users or employed as computational resources or providing sensing sensing services, uh, data collection, and so on. So the multi-tier architecture comes together with a SDN, a software-defined networks, which provides a complete network's programmability. And in this case, UAVs in higher tiers shall work cooperatively as controller units, and where and they will be responsible for collision avoidance, routing, and placement of the other UAVs. And another feature that is important is that, so in the state of the art, what we can find is that emerging applications such as augmented reality, face recognition, and mobile gaming are latency sensitive and need a high computational capability in order to be in order to provide a quality of experience and quality of service. It becomes more critical once the requirements are needed in a short time range, such as during traffic accidents such like this, emergencies, post-disaster relief, and police track services. Um, we may also have artificial intelligence over UAV fleet that support navigation of the UAVs and path planning, real-time facial recognition as well, applications such as real-time facial recognition. So scenarios like that um, require reliable path planning management, which must be considered available resources and the trajectory of every node in the scenario, in the area present, in the area nearby. This information must be jointly addressed with the computation of loading scheduling in order to meet the service requirements. For instance, during flash crowd events and unpredictable events, for example, the mobility of nodes can perform differently from the usual pattern. Thus, it's crucial to perform the task of loading service based on the mobility of each node following a prediction approach. And this prediction approach sometimes can be um, complex or sometimes can be simple. And it's also important to design a feasible prediction approach, depending on the kind of node that we are trying to track. Thus, a task offloading approach must prioritize the critical nodes. So the proposals we have seen so far in this first one, the authors developed a game theory approach to address computational tasks offloading from UAVs to nearby wireless networks. And the second one extends the computational resources of UAV swarm to the edge of the cloud, to the edge and cloud nodes. The UAV swarm placement and routing procedure are jointly optimized in order to guarantee the task communication using the edge and the cloud resources. So in this case, we have UAVs with tasks that need to be addressed by a highly resourced or highly computational resource unit node. In this case, we have in the first proposal, we have a hybrid architecture that deploy UAVs to offload ground users' tasks into available RSUs or vehicles. And UAV pre-processes the data, removing redundancies. And the second one, the proposal optimizes the UAV trajectory and bit allocation to effectively provide its resources to ground users. So the second one, we have the case where the users have to be, the tasks from the users have to be processed. And in this case, a single UAV is employed to compute this task. And in this case, the author evaluates um, the performance of the solution that is enable UAVs uh, to redirect the tasks from users or um, congested RSUs to other available RSUs. And in these last proposals, we have in this first one that minimize the energy consumption of users users and UAVs by considering the number of user offloaded bits and users and the UAV CPU frequency and UAV trajectory. So the objective is to minimize the energy consumption of the nodes and also providing a uh, offloading service. The second one, the UAV as processing works as processing units for image analysis, and the authors evaluate three UAVs and how the how is the performance of the image analysis when running in one, two, or three UAVs. And the third one, the UAVs acts as flying fog-based resource provisioning, giving access to computational resources from nearby RSUs, very similar to the previous work. And as we have seen so far, the solutions are going toward computational resource-enabled UAVs that are the UAVs that have that will have computational power to make it available to the service that has to be uh, the services that have to be running in smart city environments, for example. And energy remains a challenge, so recharging scheduling approach must be considered. User mobility is also important once the scenarios are very dynamic in a smart city environment. Besides, The deployment of multiple UVs can increase the solution scalability. However, the coordination of available resources of multiple UVs has to be investigated more carefully as the more UAVs we're using, the more complex the solution will be. And that's all for today. Thank you very much.